Okay, so here are some supplemental examples for section 6.2, which is about parallelograms. First thing, definition-wise, a parallelogram is a quadrilateral with both pairs of opposite sides parallel. So in the definition, we know it has four sides because it's a quadrilateral, and then again, each pair of opposite sides is parallel. Now there are four properties for parallelograms. One, both pairs of opposite sides are congruent. Two, both pairs of opposite angles are congruent. Three, consecutive angles are supplementary. Four, the diagonals bisect each other. Those are the theorems for section 6.2. Again, these are not part of the definition. These are the specific properties for parallelograms. Again, definition is just quadrilateral with both pairs of opposite sides parallel, and then these are the four properties. This is the example I showed you in class, but I'll just kind of throw it up there again in case you missed and you're trying to catch up. Here's a parallelogram right now in my drawing. I know these two opposite sides are parallel, these two opposite sides are parallel. And it's four-sided, so there you go, that's the definition. Now if you look, the first theorem is opposite sides are congruent. You can hopefully see the numbers here. This side's 14 points. Well, here, let's do this. Font size. Let's change the font size, I don't know, 24. There we go, everything's a little bigger now. So the side lengths here are 11.3 and 14.6. That's the first property. Second property, opposite angles are congruent. So 110, 110, 70, and 70. The third property is that the diagonals bisect each other. So you can see here, here's the middle of the two diagonals. Again, BD is one diagonal, CA is the other diagonal. BC is 7.5, or BO is 7.5, OD is 7.5. CO is 10.6, OC is OA is 10.6. Again, they bisect each other, cutting each other, each part congruent. And the thing is this, they're not all four congruent, just the two of one part and just the two parts of the other one. And then the last theorem is that the consecutive angles are supplementary. So we're talking like angle 70 degrees and 110. Those two are consecutive, supplementary. 110, 70. Supplementary, consecutive. 70 and 110. Consecutive, supplementary, and then 110 and 70, consecutive and supplementary. So those are the four theorems and properties. So anytime you're working with a parallelogram, you're going to probably use one of those four properties. Now, the first thing I'm going to start off with is a proof for this section. We do get back into proofs in Chapter 6. They're not, some of them are involved, some of them aren't involved, but they're not the real focal point like it was in Chapter 4. They're just more there to kind of, hey, look, we can do some proofs. So here we go. Give myself a little more room to write. So the first thing we have given to us is that we have two parallelograms in the drawing, which means we have all those properties of parallelograms that we had for today. So opposite sides congruent, opposite angles congruent, consecutive angles supplementary, diagonals bisect each other. Now in this problem, what I'm trying to do is prove that angle F and angle A are congruent. I want to show that they're the same. So I want to talk about congruent angles. So that means I don't care about opposite side lengths, I don't care about diagonals, I don't care about any of that stuff. And I'm also trying to show that they're congruent, so I probably don't want to mess with the consecutive angles because that means you're supplementary. So the first thing to recognize in this problem is these two shapes do have a pair of congruent angles in them, angle BCH and angle DCG by vertical angles. So that's my first start. Now once I catch that, it's hopefully pretty easy to figure out where this is going to go. Angle A and BCH, hey, they're opposite angle pair in a parallelogram. Therefore, they're congruent. And angle F and angle BCG, hey, they're also a pair of congruent angles because of the fact that they are opposite angles in a parallelogram. And now, hey, if all four of those are congruent by some transitive properties, A is congruent to F. Now, this is a little trick that I used in college quite a bit. I got tired of always doing DCG and BCH. So what I would do is I would just number it. I'd make my own number up. Angle 1 and angle 2. That's okay to do, actually. So now I don't have to worry about the all the business of getting caught up in statements, not R. As his statements, R as reasons, and all the three-letter names. So first of all, given, I'm feeling lazy this evening. Throw right in there. Step 2, I know I have a pair of congruent angles. So angle 1 is congruent to angle 2, the vertical angles theorem. Okay, so vertical angles theorem. Step 3, Step 3, I also know that angle A is congruent to angle 2, and angle 1 is congruent to angle F. And you could just say opposite angles of a parallelogram are congruent. Okay. Now, again, one of the important things about this problem is we had to know first that it was a parallelogram that was given. If we didn't know that, we couldn't use reason 3. Now becomes the arduous task of, okay, well, if 1's congruent to 2 and A is congruent to 2, it means A is congruent to 1 by the transitive property. And now if angle A is congruent to angle 1 and angle 1 is congruent to angle F, angle A is congruent to angle F, by transitive property. So this does liken back to the proofs we did in chapter 4, but now we're doing with parallelograms. Okay. Next example, just kind of one that I noticed people struggle with in the past, is a problem like number, well, this isn't number 1, this is actually from a worksheet. You've got here a parallelogram, and your job is to solve for x. Now the issue is, the other part is y. So there are a couple ways to get to x and y, but probably the most direct route is actually getting to y first, realizing, hey, those are opposite angles, so they have to be the same, meaning that y is 44 degrees. Now for x, you could either think of angle y or the angle k there, the angle m or the angle k with y or 44. Either way, it doesn't matter since this is 44 as well. But these are consecutive angles, J and MR, J and KR. So these two have to add to 180, these two have to add to 180. So if I take 180 and subtract 44, I get 136 degrees. That has to be x at 136. Now the last example I want to go through is number 30 from the textbook. We only need to do parts A and B. I just cut all 3 parts out from the book for this sheet because it kind of matched up nicely. So we want to use the graph shown to do a couple of things. One is to use the distance formula to show that they bisected each other. So what I have to do is recognize where the points are. Now point L is at -1, -1. Point K is at 2, 5. J is at -4 or 5. M is at -7, -1. Sure that's right. Wait. Oh, it's -8. And this is -5. Make sure it's up 5. Okay, good. Alright, so there's all my length. There's my points, except the last point, which is the most important point for this, point P. Because I basically got to figure out the distance for all of these to point P. So 1, 2, 3, 1, 2. So -3, 2. So it says it wants us to use the distance formula to determine if the diagonals bisect each other. So all I have to do is do the distance from J to P and P to L, K to P and M to P. Now, just because otherwise you're going to stare at me doing the distance formula for 5 minutes, I'm just going to say I worked it out. And what I get for distance for JP is the square root of 13. Okay. And then when I do the length of PL, I get also the square root of 13. Okay. So this is part A still. So far, P is the midpoint of J and L. Now the next question is, well, is it the midpoint of K and M? Well, let's see. KP has a length of root 34, and PM has a distance of root 34. Neither of those simplify, which you wouldn't have to worry about that anyway, even if they did, because we just care about making them equal, which they are. So, yes, they do bisect each other. Each part is congruent. Now, part B asks, are the diagonals congruent themselves? And the answer is obviously no. This guy's root 13 plus root 13. Km is root 34 plus root 34. That's not the same as this one. So no. Not the same lengths. Okay. And so that's a little bit extra work there. Again, I didn't use the distance formula. I just was being short and lazy. If you don't remember the distance formula, it is this. D equals the square root of x sub 2 minus x sub 1 squared, y sub 2 minus y sub 1 squared. And so you'd plug in negative 5 minus negative 3, square it, plus 5 minus 2, square that. Add them together, take the square root. You'd be good. Okay. All right, so that's that.